Equations are amazing. Equations are wonderful. Equations allow us to explore possibilities that aren't practical without spending a lot of money, to theorize about things before we try them out. But as useful as physics equations are, they can also be seemingly kind of boring, especially if you have no idea where they come from. Stephen Hawking called equations the boring part of mathematics. He said that he attempts to see things in terms of geometry, in terms of shapes and graphs. So that's what we'll try to do today. We've already talked about how the slope of the displacement graph gives you the velocity, and the slope of the velocity graph gives you the acceleration. We've also talked about how you can go the other way by finding the area under the curve. So instead of me just giving you equations and you taking my word for it that they make sense, we're going to use graphs to prove or derive the equations. So at this point we already have a couple of equations. We know that speed is distance divided by time, which is kind of similar to the equation velocity is displacement divided by time. Very simple kind of self-explanatory equations. If you travel 10 meters in 5 seconds, then 10 divided by 5 gives you 2 meters per second. Which makes sense because you traveled 2 meters each second. 2, 4, 6, 8, 10. 5 seconds, 10 meters. We've also said that acceleration is the rate at which your velocity changes. It's the change in velocity divided by time. Both of these things are the slopes of the graphs we talked about. Rise over run for this graph is a displacement over a time, giving you velocity. Rise over run for this graph is a change in velocity divided by time. Change in velocity divided by time is acceleration, which is why the slope of this graph is acceleration. But now we need to move on to more complex equations. The equations we're going to derive today are called the equations of constant acceleration. And we can use these same ideas of slope and area to derive these equations too. Galileo was the first person to do this, although he had much less knowledge of physics than we do today. At that point it was more like a mathematical proposal, and it needed experimental evidence to prove it. Sagredo, one of his contemporaries, said the following: "Although I can offer no rational objection to this, or indeed to any other definition devised by any author whosoever, since all definitions are arbitrary, I may nevertheless without defence be allowed to doubt whether such a definition, as the foregoing, established in an abstract manner, corresponds to and describes that kind of accelerated motion that we meet in nature in the case of freely falling bodies." In other words, they thought it was a very nice thing that Galileo had derived, but he didn't know if it actually had any connection to the real world, to the way things actually fall. As a scientist, Galileo would have to prove that his equations worked in the real world. But back to that later. Just like Galileo did, let's derive them first. As I mentioned, these equations are called the equations of constant acceleration. So let's start with graphs that show a constant acceleration. This, for example, would be like a ball falling, a constant negative acceleration towards the ground. But negative signs could confuse things, so let's go with a positive acceleration like this. And just to make sure our equations work for all situations, let's have two different accelerations. So we have one acceleration for a little while and then a slightly different acceleration after that. Here are the equations of constant acceleration that we are going to derive. Let's take them one at a time. This equation is really just the definition of acceleration. We've already said that acceleration is change in velocity divided by time. Change in velocity is equal to Vf minus Vi. So this is really something we already know. To derive equation 2, let's take a look at a velocity graph. This velocity graph shows two different accelerations, just like the acceleration graph I showed you a minute ago. It has one acceleration that's high and one acceleration that's a little bit lower. Now what we're going to do to derive this equation is that we're going to come up with an equation for the displacement in this period of time t. To find the displacement in this period of time t, since this is a velocity graph, we can take the area under the graph, the area under the line. In this time period t, the area under the graph is this area here. That's made up of a triangle and a rectangle. The rectangle is just VIT. VI is the vertical side of the rectangle, and T is the horizontal side of the rectangle. To get the area of a triangle, you have to do half of base times height. So 1/2 multiplied by T, which is the base, multiplied by Vf minus Vi, which is the height. Vf is the final velocity and Vi is the initial velocity. If we take one number away from the other, we get the height of the triangle. That might be a little bit confusing, but if you imagine that Vf and Vi were two numbers, such as 10 and 4, then the distance between them will be 10 minus 4, which is 6. So if we take one away from the other, we get the height of the triangle. Then to get the total area under the graph, we add these two things together. VIT plus 1/2 T multiplied by Vf minus Vi, and that is the total area under the graph. Then what we can do is take the first equation that we already know and rearrange it to make it Vf minus Vi equals. If we multiply both sides of the equation by T, we get Vf minus Vi equals At. And then we can substitute that At into the equation that we've just written below. We can replace the Vf minus Vi in the equation below with At. Once we've done that, the final step is just to multiply out the brackets. We have a half t multiplied by at. The two t's become a t squared and we get a half at squared. So the final equation is x, displacement, is equal to vit plus a half at squared. Vi is the initial velocity, t is the time period, a is the acceleration. So that's equation 2. Now we'll move on to equation 3. To derive equation 3, we do a very similar process, but instead of using Vf and Vi, instead we're going to take an average velocity right in the middle. By drawing a line across this average velocity, we can see that if we take this little triangle at the top and fit it into the gap here, we end up with one big rectangle. So instead of using the triangle at the top, we now have one big rectangle that's exactly the same area as it would have been if we had taken the triangle and added it to the rectangle like we did the first time. To get the area of a rectangle is really simple. We just take the height and multiply it by the width. The height is just this average velocity that we marked, v average, and the width is the time t. So the displacement is equal to the average velocity multiplied by the time t. Next step, we need to get rid of this average velocity. We don't want that in the equation. So this object started at an initial velocity vi and ended at a final velocity vf. Right in the middle it had an average velocity, v average. To find the average velocity, we can take the initial velocity, add it to the final velocity, and divide it by 2. Think about it this way. If an object started at a velocity of 0 and finished at a velocity of 10, you would do 0 plus 10 divided by 2 and get 5. 5 will be the average velocity, right in the middle of 0 and 10. So we have an equation for the average velocity that we can now plug into our equation for the displacement, x equals v average times t. If we plug it in here, we get our final equation, our third equation, which is x, the displacement, is equal to vf, the final velocity, plus vi, the initial velocity, divided by 2, all multiplied by t. So that's equation 3. To get equation 4, the first thing we need to do is go back to equation 1. We rearrange equation 1 to make t the subject, and we'll get t equals vf minus vi over a. Next step, we also need to use our third equation that we derived just previously, x equals vf plus vi over 2 multiplied by t. We substitute this first equation for t into our third equation. If we do that, we get x equals vf plus vi over 2 multiplied by vf minus vi over a. These are two fractions. We can multiply them together and make them into one fraction. The bottom's easy, 2 times a is just 2a. The top, we have to multiply out these brackets. If you're not sure how to multiply out brackets, it would be a good idea if you talk to me and we'll go through it. But when you multiply out these brackets, you end up with vf squared minus vi squared plus vi vf minus vi vf. At the end of this, we have a plus vi vf and a minus vi vf. Those cancel out to 0, just like plus 3 minus 3 is 0, and plus 7 minus 7 is also 0. We end up with x equals vf squared minus vi squared over 2a. If we multiply both sides by 2a, we get 2ax equals vf squared minus vi squared. And last of all, we rearrange it to make vf squared the subject. Vf squared is equal to vi squared plus 2ax. And that gives us our fourth equation. Finally, equation 5. I'm not actually going to derive this one because it's really similar to equation 2. Basically, to derive equation 5, you do exactly the same thing that we did with equation 2, but with the reverse graph. Instead of a graph where the velocity is increasing, do it with the exact same graph reversed so the velocity is decreasing. When you do that, you get x equals vft minus a half at squared. And there we have it, the 5 equations of constant acceleration. Here they are presented in a table. You'll notice that each equation has one variable of the 5 that is not present. Any question you face using these equations will give you 3 variables and ask you to find a 4th. There will always be a 5th variable that isn't mentioned anywhere in the question. By figuring out what that 5th variable is, you can easily figure out which equation to use. So if in a question you're given 3 numbers and asked to calculate a 4th, if you find the equation with those 4 things in it, whichever one of these equations has the 4 things that you either know or want to find, then you can solve the problem. So there you have it, 5 equations that you can use to solve problems in any situation where the object has a constant acceleration. Of course, Galileo then had to design an experiment to prove those equations, to prove that objects really fall that way. Timing an object falling is actually kind of difficult even for current physics students, and at that time it was even more difficult. So Galileo used a physical slope instead. He timed how long it took for a ball to roll down a full slope, and then half a slope, and then quarter a slope, and all different combinations, all different lengths. And then he tried it for different slopes, increasing the slope, a really steep one, a shallow one, all different angles. And he found that the motion was very similar. In all those cases, he found a constant acceleration. An object that's just falling, a free-falling object, would be kind of like having a slope that was 90 degrees. And Galileo concluded that if 60 degrees showed a constant acceleration, and 70 degrees showed a constant acceleration, and 80 degrees showed a constant acceleration, then it made sense that 90 degrees would also be a constant acceleration. And in that way he showed that his equations accurately described the motion of a falling object. And also, because the speeds in his experiment were so slow, air resistance had no effect on the results. Now it's time to practice. If you're not one of my in-class students, you can go to flippedphysics.net and find some materials to practice with there. If you are, I'll see you in class. And in physics, practice is the key to success, so hop to it. Thanks for watching Flip Physics. Please leave your questions, thoughts and suggestions in the comments below, unless you're just going to tell me to shut up, Wesley. But either way, I'll be happy to respond and answer any questions that I can. You can also feel free to subscribe and like and do all that good stuff, and materials can be found at flippedphysics.net.